Simple microscope. Have you ever seen an instrument which is used to observe the fingerprints on a page? Or to study various maps? This is a device which makes things look larger than they actually are. It is just a simple magnifying glass, also known as a simple microscope. It consists of a biconvex lens of small focal length mounted on a wooden or metallic frame with a handle. Let us see the principle and the working of a simple microscope. Principle. When an object is placed between the first principal focus F and the center C of a convex lens, the rays emerging from the object do not converge, but they seem to converge at a point by extending backwards beyond the lens. The image obtained is erect, magnified, and virtual. In such a case, the object and the image are on the same side of the lens, and hence it is not possible to get the image on a screen. The image should be observed from the other side of the lens. Working. When we bring an object closer to our eyes, there is a certain limit up to which the object can be clearly seen. This limiting distance is known as the least distance of distinct vision, expressed by d. Suppose an object AB subtends an angle alpha at the eye. When it is at the least distance of distinct vision d, we try to bring the object closer than that limit. The image becomes blurred. Hence, we place a converging lens close to the eye and move the object closer than the least distance. Here, when an object lies between the lens and its principal focus, a virtual, erect, and magnified image is obtained at the least distance of distinct vision. Suppose beta is the angle subtended by the image at the eye. Then the magnifying power m of a simple microscope is given by beta upon alpha. That is, the ratio of the angle subtended by the image at the eye to the angle subtended by the object at the eye when both are at the least distance of distinct vision. Therefore, m is equal to beta upon alpha. The magnifying power can also be given as the ratio of image size to the object size. Therefore, m is equal to a-b' upon ab. In practice, angles alpha and beta are small, so the magnifying power can also be given as m is equal to cb' upon cb. Suppose cb' is equal to v, and cb is equal to u. In this case, v is equal to d. Hence, m is equal to d upon u. For further calculations, we can derive m is equal to 1 plus d upon f. When an object is placed at the focal length of a lens, then the final image will be formed at infinity. Here, as the image distance is very large, that is infinity, in the above equation, 1 can be neglected as compared to d upon f. Therefore, the magnifying power m is equal to d upon f. From this equation, it is clear that the magnifying power and the focal length of a lens are inversely related to each other. Therefore, smaller the focal length, larger the magnifying power.